Well, thank you, Dawn, and thank you all for joining us this afternoon. This afternoon, we're going to talk. We're going to we're going to talk a little bit about low carbon hydrogen, the good, the bad, and well, the not so good. We're going to talk about hydrogen very briefly. We're going to talk in some detail around the challenges associated with transporting hydrogen to distant markets, and importantly, not just talk about the challenges, but hopefully introduce potential solutions in the form of liquid organic hydrogen carriers. And critically, I think, does this liquid organic hydrogen carrier thing offer a business opportunity for the petrochemical sector in Canada and here in Sarnia-Lambton? So, without further ado, on the agenda, the promise and issue with hydrogen. So, jurisdictions across the world, something like 100 of them, are preparing hydrogen strategies, plans, how it is we can grow a low carbon or even green hydrogen manufacturing sector to supply not only domestic markets, but also distant markets. And why hydrogen? We're all familiar with if you use hydrogen as a fuel, you get two things: a whole lot of energy being released, as well as water. The good thing, there's no CO2 associated with the use of hydrogen as a fuel. The other good thing about it is on a mass basis, and I'm very careful to say on a mass basis, hydrogen is the most potent fuel we have outside of nuclear fuels. It's the most potent chemical fuel that we have. On the not so good side, though, is related to its density. And as you'll see, we pretty much have to buy hydrogen by volume. We don't buy it by mass, and I'll explain that comment in a second. On a volume basis, hydrogen is the lowest energy dense material that we have, presenting a challenge. If the energy density is low, the material density is low. And so how do we transport commercial bulk volumes of hydrogen to distant markets? And does this not so pretty property of hydrogen present a business opportunity for, in particular, the petrochemical sector? So to drive home this density question, imagine for a moment that you had a container of liquid hydrogen. This is a very specialized and expensive container. And in this case, for imagination purposes, this container contains 50 liters of liquid hydrogen. We have a more familiar container, on the other hand. It says a gasoline container containing conventional gasoline. Gasoline, as we all know, is a hydrocarbon, so gasoline contains hydrogen. And in this case, we have 50 liters of gasoline and 50 liters of hydrogen. So my question, this is going to be on the quiz. The question: how much hydrogen, or which container contains the most hydrogen? Now, you can probably tell by the context that it's going to be the gasoline container. The gasoline container contains meaningfully more hydrogen than does a container of pure liquid hydrogen. And the reason for that has to do with the density. The density of gasoline is more than 10 times as high as the density of liquid hydrogen. Gasoline contains well over 10% hydrogen, ergo, it contains more hydrogen than a vessel of pure liquid hydrogen of the same size. And this becomes a very important feature or characteristic when it comes to transporting hydrogen. So just a couple of points on transportation fundamentals. What I'm showing here is a cement truck. Cement is very dense, very high density, and as a result, you can only get so many cubic meters on this truck before you will arrive at the truck's load limit. So we are load limited or mass limited. And you can tell by the size of the truck, it could be bigger, but you can't get more tons on it anyway, so why make it bigger? And look at the wheels, 14 wheels on this thing, 14 very heavy-duty wheels required to carry a few cubic meters of cement. Now, on the other hand, what if we're carrying something not so dense? Oh, like potato chips, very low density. Now, this trailer, you can pack as many cubic meters of boxes of potato chips on this truck until it's full, and you won't meet its load limit, even with the tiny little wheelbarrow wheels on the back of this thing. That's because potato chips have a very low density. So if we're moving potato chips, we're volume limited. We're not going to get too much weight on this. This tractor can't pull this trailer. Now, I don't know if we can all imagine if you had a bag of potato chips in your hand and you dropped it, what would happen? Well, it would fall to the ground because it's heavy compared to hydrogen. If we had a a bag of hydrogen, otherwise known as a balloon, and release it, it would float away because the density of hydrogen is so low, much lower even than potato chips. So the concept here of being mass limited versus volume limited is kind of important. And so now that we've got that behind us, let's put some numbers in front of us. What we have at the bottom, this white trailer, is a typical commercially today tube trailer. The trailer's quite heavy. These wheels are not wheelbarrow wheels. The reason it's heavy is because these tubes contain hydrogen at 300 bar, hydrogen gas, or well over 4,000 pounds per square inch. So with very high pressures and at ambient temperature, more or less ambient temperature, what does this truck carry? Less than a ton of hydrogen on a tube trailer like this, less than 1 ton. Now, this trailer above, the gasoline trailer, is not designed to carry hydrogen. It's designed to carry gasoline. But this gasoline embedded in it as part of the gasoline molecule are over 4 tons, or roughly 4 tons of hydrogen. So this is what we mean by a hydrogen, liquid organic hydrogen carrier. Gasoline or chemicals like gasoline or hydrocarbons, they contain hydrogen, and because of the density differences, can contain actually more hydrogen than certainly a compressed hydrogen trailer, as we're showing here. Now, my talk today is really about transporting bulk hydrogen from all of this new hydrogen manufacturing, low carbon hydrogen manufacturing infrastructure that governments and various organizations want us to build. How are we going to get this stuff across oceans, especially given the density issue or question that I'm pointing to? Pipelines, we're not going to be building pipelines across oceans, and we're certainly not going to send the hydrogen by air freight. So what are we going to do here? By the way, just on a sidebar on hydrogen, there's it's the issues and challenges and opportunities associated with moving hydrogen modest distances by pipelines are well understood. Companies like Enbridge and organizations like the IEA and EIA and a whole bunch of others have done a lot of work around moving compressed hydrogen either by repurposed natural gas pipelines or purpose-built new hydrogen pipelines. One of the points that have come out of this work, these studies, is that there's a limitation on how far, an economic limitation or crossover point around shipping hydrogen by pipeline, and that is distance. And I'm sure that there's lots of variables at play, but notionally, if you're going to be shipping hydrogen under 1,500 kilometers, pipeline is probably the way to do it as a compressed gas. If you go beyond 1,500 kilometers, you might want to start looking at other ways to carry the hydrogen, as in liquid organic hydrogen carriers. And so, and because we're not going to build pipelines across oceans, I'm not going to be talking anymore about pipelines today. And so is there a more efficient way to move bulk hydrogen across oceans other than as either, well, they're certainly not going to do it as a compressed gas, but even as a liquid hydrogen. And if we're not going to use air freight and pipelines, we're kind of stuck with ships. So I'm going to show you and discuss in the context of liquefied natural gas carriers. And to be crystal clear, and I'm going to say this several times, a liquefied natural gas carrier cannot be used without really expensive modifications, probably too expensive to even contemplate, to carry liquid hydrogen. However, we're volume limited, so let's talk about a typical 150,000 cubic meter LNG carrier. And as I said, it's volume limited, so you can load up this ship to 150, and you'll be carrying, when you consider the density, a little over 60,000 tons of LNG. If you're transporting energy, if that's really what you're after, then you're well over 3 petajoules per cargo. Now, if we had a liquid hydrogen carrier of the same volume, again, this technology will not work for hydrogen, liquid hydrogen. But let's just say we had a ship of 150,000 cubic meter payload, translate that into tons of hydrogen delivered, it's only 10. It's like 1/6 the amount of hydrogen on this ship, this imaginary ship, and delivering about half of the energy cargo. So you can see that the economics around moving LNG by ship makes sense. How do I know that? Well, because people are doing it. This is an ongoing business with a future. Shipping hydrogen by liquid hydrogen by ship is an unanswered question. Why would this difference? They're both liquids and they're both cold. Well, this is really cold. Liquid hydrogen is at minus 253 degrees C. That's only 20 degrees C above absolute zero. The technology and techniques and equipment and materials required to do this are very different than it is for LNG, which is operating at a relatively balmy minus 162 degrees C. So where are we with liquid hydrogen shipping? There is at least one ship, well, there's only one I know of, and I'm not too sure if I'm going to pronounce this right, but it's called the Susio Frontier. Susio, if I pronounce that correctly, is the Japanese word for hydrogen. And this is a purpose-designed ship designed to move liquid hydrogen. In this case, it's going from Australia, the hydrogen being produced by gasifying coal. In any case, they're moving liquid hydrogen from Australia to Japan. And, in terms of commercial and global scale shipments, this thing has a whopping 1,250 cubic meters of liquid hydrogen on board compared to a couple of orders of magnitude higher for an LNG ship. Is because the volume is volume limited. You fill this thing up to 1,250 cubic meters of liquid, you're carrying something like 90 tons and 3 orders of magnitude, whatever, a lot less energy on this ship compared to, and so we really don't have any way to ship liquid hydrogen in huge volumes, at least across oceans or even long distances, say well over 2,000 kilometers. And so what are we going to do? Well, visionary people, Total, the French oil giant, has some kind of an arrangement with at least 3 marine or shipping companies looking at building a 150,000 cubic meter liquid hydrogen ship. Now, this thing is in the exploratory stage, as far as I know. Nobody's laid a keel or anything like that. Today, there is no ship that I'm aware of that can carry large commercial volumes of hydrogen in the liquid form. The Bowman Center has been working on hydrogen now for several years, and about a couple of years ago, we engaged Queen's University to take a look at the state of the art of chemical carriers at the time they did the study, at least, and report back to us. And they did. They prepared a meta study. This study is available by contacting the Bowman Center. And they looked at metals as a carrier, like lithium metal hydride. They looked at inorganic liquid hydrogen carriers. For example, the best known one is ammonia. And they also looked at a variety of different types of liquid organic hydrogen carriers. And depending on what the customer really wants, ranked these carrier options based on safety, technology, readiness level, cost, societal acceptance, risks, hazards, all that sort of thing, and put it in a matrix and generated favorites. And their favorites were 2 that I'm going to talk in a little bit of detail about, dibenzyl toluene and toluene, but as well as ammonia and methanol. So let's just discuss those very briefly. First of all, who is our market? If we're talking about you want to buy energy, say methanol or ammonia might be more effective carriers than the type of carrier I'm talking about today. If you want to burn the fuel, perhaps ammonia is the best way to go. But if the customer, for whatever reason, wants hydrogen, they don't want ammonia, then ammonia and methanol aren't as favored, because although, well, first of all, we need to recognize that it takes a tremendous amount of energy to to make ammonia, and maybe less so, but still a lot of energy to make methanol. And if you want to strip the hydrogen off, you destroy the molecule. If you strip the hydrogen, it can be done. I think the technology is well understood, but I don't think it's commercial. At least I'm not aware that it is. But if you did just strip ammonia, hydrogen from ammonia or from methanol, you destroy. In the case of ammonia, you get hydrogen and nitrogen. In the case of methanol, you get hydrogen and CO2. And so so they become single-use carriers. If the customer wants hydrogen, though, not the chemical ammonia nor the chemical methanol, then we would be looking at recoverable hydrogen, as well as can these chemicals be reused rather than have to resynthesize them and all of the emissions and energy associated with manufacturing the chemicals. So where are we? If we're going to reuse the chemicals, then I think we need to, I suggest that we think of the candidate chemicals as couples. One is a form of a rich hydrogen or low in hydrogen content, and another version of the same chemical or similar chemical that would be rich in hydrogen. And in this context, the Queen study identified two in particular, and which now we're going to talk to in a little bit more detail. Now, yeah, sometimes when you watch the news, the commentator will say something like, the upcoming video contains graphic or could be offensive material. Well, the upcoming next two slides are going to be technically kind of difficult, and so be forewarned. But I encourage you to stick with me because these two slides explain the whole foundation for what it is we're talking about when we refer to liquid organic hydrogen carriers. So the first one is called toluene. And this thing, it's kind of ugly looking on the screen, I'm sure, is lean in hydrogen. You can see it does contain hydrogen. It's characteristic of the chemical toluene. This little group here is called a methyl group, and it contains a certain amount of hydrogen, and it is the lean version of this chemical. But through processes that are well understood today, no research required, you can add hydrogen to this molecule to create a different molecule. This one is rich in hydrogen, and we're not going to count them. You can take my word for it, but you can see there's a difference in the amount of hydrogen between these two molecules. How many? 6. There are 6 recoverable hydrogen atoms on the rich version of the chemical. So if you had this chemical and you were to dehydrogenate it or harvest the hydrogen from this molecule, you would end up with the original molecule, this toluene. So the two chemicals, toluene and methyl cyclohexane, you can see there are 7 carbon atoms here, 7 here, but there are 8 hydrogen atoms in this version, 14. So there is recoverable hydrogen, and the technology to these arrows indicate that these are reversible reactions. Why is this important in the context of our discussion on transportation? First of all, I'm going to repeat, the processes to do this are well understood. In fact, every refinery, any fuels refinery in existence on planet Earth today makes toluene, and they make a lot of it. Why? Because it's high in octane, and so it's added as an octane enhancer. They also produce toluene as a chemical precursor for all kinds of products. But that's not the main. The technology is there. It's proven. The technology readiness level is 9, if you're familiar with that term. What's really important is if we're transporting these 6 hydrogen atoms can be transported in the form of this methyl cyclohexane chemical using existing gasoline infrastructure without alteration. Let me rephrase that. Without alteration. You can use existing gasoline pipelines, existing rail cars that move gasoline, existing trucks and trailers and ships. Without same pumps, same seals, same piping, same safeguarding. It's identical. You don't need to do anything. You don't need to build a specialized ship that can keep the product at minus 253 degrees. You just take it from existing transportation inventory. Toluene is a little bit hazardous. It is a component in gasoline, but on the good side, we have over 100 years experience in safely handling toluene in an environment and in an environmentally sound way. Key is it's reusable. These 2 arrows back and forth suggest this is not a suggestion. These are reversible reactions through different, well understood in the petrochemical industry processes. The other chemical that that the Queen's report discusses is this thing. Now, I didn't show you all the hydrogen because this was already messy enough with methyl cyclohexane. But the little arrow here at the top is actually, that's the methyl group. This is called a benzyl group. Another benzyl group, this thing here is toluene. So the name of this chemical, dibenzyl toluene. This is the lean version of this chemical. So there's lots of hydrogen on here. We'll see that in a sec. The rich version has, instead of 1 carbon on each one of these corners, this one has 2 hydrogens at each corner, meaning that this thing can move 18 recoverable hydrogen atoms. And the chemical, again, dibenzyl toluene. The name of this chemical is perhydrodibenzyl toluene. We're going to refer to this couple going forward in today's discussion as DBT, short DBT. When I say DBT, I'm referring to the couple. And when I say toluene, going forward, I'll be referring to the toluene methylcyclohexane couple. So this DBT couple has the following advantages that are very similar to the gasoline version or the toluene version. Uses existing technology. Refiners and petrochemical, they know all about this conversion, the chemical processes to manufacture the chemical. In fact, dibenzotoluene is being produced today for and is used in heat transport fluids. It's a very stable chemical. The rich version is it's like diesel fuel. I haven't really checked into it. My guess is that the rich perhydride would make excellent diesel fuel, as is. Meaning, as with toluene couple, you don't need any specialized equipment to transport this. This can be moved by ship. Existing diesel, any ship that can carry diesel fuel can carry this stuff, or rail car, or pipeline, or truck trailer. Same pump, same seal, same everything. No extra investment required, other than maybe give the equipment a bath before converting it to this service. The nice thing about this couple DBT is it's compared to toluene, it's pretty much non-hazardous. It'd be very difficult to get this stuff to burn. It has a really low vapor pressure compared to toluene. If you threw a match in this stuff, the match would likely just go out. As with the toluene couple, this is reusable, as indicated by the two arrows. So that's kind of the chemistry behind this thing. I want to just digress for just a moment. The Bowman Center did not invent this. This is not something, this isn't our brilliant. People around the world are working on this. It's not clear to us, at least, that anybody in Ontario or Canada is doing much in the way of this thing. Referring back to our truck, and we're going to show a picture in the context of LOHCs. Remember our 4,000 PSI truck carrying roughly a ton of hydrogen? There's a company called Hydrogenius who's all over this. They've been working on it for years. They are offering commercial hydrogenation, dehydrogenation, and have pilot facilities, several of them operating in Europe, testing out this idea. So if we are the Bowman Center, if we're right that there's really not a whole lot, we are actually behind. If we want to move on this, we first have to catch up and then take a leadership role, hopefully. This trailer, using the technology we're talking about, is transporting almost double, or roughly speaking, double the amount of hydrogen from its hydrogenation site to the customer's dehydrogenation site. And now Hydrogenius is not using toluene. They are very much sold on the idea of the DBT couple. So we talked about transoceanic shipping in a very not valid comparison using LNG as a carrier. But this picture on the screen is a standard run-of-the-mill 150,000 cubic meter gasoline diesel ship. And so if it was carrying 150,000 cubic meters of gasoline, that's what or diesel, that's what would happen on board. If it were transporting liquid organic hydrogen carrier, either of the two I'm talking about, the cargo would look like 20,000 tons of recoverable hydrogen, compared to a non-existent in terms of technology liquid organic hydrogen carrier ship. So 20,000 tons is the payload here, more or less double what it would be if a liquid hydrogen ship were available to us. It's not. So I've kind of in a fragmented way talked about density, and I talked about hydrogenation, dehydrogenation, lean version, rich. Let's put this thing all together. Let's stitch it all together, and I'm going to show you how this all works in one slide. So first of all, we have to have a supply of lean liquid organic hydrogen carrier. Petrochemical sector, this is up to you to develop and make the supply available, not just for Ontario, but for the world. We also need a supply of low carbon hydrogen. Green hydrogen is what seems to be in demand in Europe. We need a hydrogenation plant. Now, I'm going to say it again. I've said it before. Liquid organic hydrogen, this type of process unit and the process are well understood, commercially available by a number of companies who sell processes for petroleum refineries. So we feed the lean liquid organic hydrogen carrier, say DBT, to this unit or toluene. We supply the same unit with the hydrogen, And what we do is we convert the lean version to the rich version of the liquid organic hydrogen carrier. Now, without any special equipment other than the equipment that's available today, we load our conventional ship onto with our rich load hydrogen bearing chemical onto the ship. The ship makes its way to the customer, say in Europe or Asia, where the customer would then have the hydrogenation plant. Now, if for people in the refining business who are on the call, this is a reformer. It's like a gasoline. Every refinery has one. You need them to increase the octane of the feedstock to meet the octane specs of gasoline. And one of the products besides a high octane product, reformers produce hydrogen. Now, in our case, because we supplied it with green hydrogen, it will deliver green hydrogen, which is what the customer, or low carbon hydrogen, which is what the customer wants. And in doing this, it reproduces the lean liquid organic hydrogen carrier that we started with. The ship will probably wait while this is happening. And when it's complete, the customer will load the the liquid organic hydrogen carrier back on the ship. The ship will then go back to the original port for a recharge of hydrogen. We don't need to build a new ship every time we transport a product across to a market, and we will not need to produce new lean or organic hydrogen carriers because it'll be reused. And so what we have here, when I look at this, I look like, this looks like LOHCs could be part of a circular economy. A circular economy being a topic for a different day, but this seems to fit in with a direction that a lot of people want our economy to move in. I've been talking a little bit about at the outset about jurisdictions, like more than 100 of them today, have strategies and plans to create a new low carbon hydrogen manufacturing industrial sector. And even that's right here in Sarnia, in Ontario. The Sarnia-Lambton Economic Partnership hosts a committee who's looking at turning our region, Sarnia-Lambton, into Ontario's hydrogen hub. There's a lot of work going on this topic, but less so on the transporting of this product in production in excess of domestic demands. The picture at the bottom, the hydrogen roadmap, that is from Alberta's hydrogen roadmap website. The one above it, Ontario's low carbon hydrogen strategy, published about a year and a half ago, I think, talks again about how we in Ontario are going to develop a world scale low carbon hydrogen manufacturing capacity. Neither one of these documents talk about how we're going to get it to market. There's not a mention of it. And so there seems to be something missing here. The document on the left, the Hydrogen Strategy for Canada, is a little different. Now, it was published in December of 2020, and that document does mention one paragraph, I think it is, out of 40-some, almost 50 pages, around transportation. And in that document, they make reference to liquid organic hydrogen carriers. And in the same paragraph, they talk about liquefied natural gas and the potential for converting that infrastructure to liquid hydrogen. But at least they mention it. So I'm showing this slide because what I really think I'm saying here is there appears to be an unmet need. There appears to be an opportunity, if we're going to develop a world-scale hydrogen export business, an opportunity for particularly petrochemical industry to take advantage of that and hopefully make it profitable. When? Well, a year ago last August, so 13 months ago, Canada signed an agreement with Germany. Germany is thinking they're going to need far more hydrogen than they will be able to manufacture domestically. And so Germany, like other countries, are looking at countries like Canada who could develop the capacity to augment their domestic supply of hydrogen. And so we have an agreement. We're going to start shipping low carbon hydrogen or green hydrogen, probably to be manufactured in the Maritimes, Newfoundland, Labrador, to Germany. But how are we going to do that? And we're going to do it in 2 years. Shipments are supposed to start in 2 years from now, less than 2 years from now. And one thing I think we can be crystal clear: there will not be any world scale liquid hydrogen ships available. And we've all agreed we're not going to send it by air freight, and we're not going to build a pipe. So what are we going to do? How are we going to meet this commitment? And I'm suggesting that, or the Bowman Center is suggesting that maybe there's an opportunity here to do it via liquid organic hydrogen carriers and using commercially readily available hydrocarbon fuels carriers to move the LOHC. So we're getting close to the end here. Shipping bulk, like, what could come of that? Well, first of all, even the federal strategy suggests that there might be some development. I would not call it research and development, but it could be some development work or IP development that would be Canadian owned. For any business development folks that are on the call today, there could be an opportunity here for a whole new outlet for a new chemical. And of course, it would have to be accompanied by profits. One thing I'll mention, DBT is current. I've already mentioned is being commercially produced today as a heat transfer fluid because of its very high temperatures. It's a very stable chemical. The price of DBT today is about $5 a kilogram. $5 a kilogram, almost an order of magnitude higher than the price of toluene. So you should give that some thought. As the world is decarbonizing as the electric transportation system far faster than anybody would have ever dreamt of only a couple of years ago. And at some point, we're going to need less gasoline and diesel fuel than we have today. And if we want to, and these chemicals, though, are extractable for crude oil. So it could be that we could use fuels that are products that are contained in crude oil that are currently destined for combustion as part of transportation fuel, but divert them from the fuels pool to these new purpose-designed petrochemicals designed to move hydrogen. Doing this will enable, if we can do it, enable the Canada-Germany agreement, and if we have the capacity, lead to other agreements. And like I said, this is something that the petrochemical industry, if they see an opportunity here, including here in Sarnia, Lambton, could be doing this. Even if we don't make the hydrogen here in Ontario, we'd be shipping the LOHC to the green hydrogen source. That's in this case for the German would be the Maritimes. So just to drive home a point again, the petrochemical industry in Sarnia, maybe there's something here that the business development people could be looking at. And it's not for today. You know, Wayne Gretzky is, I think, credited with saying, don't look at where the puck is, look at where it's going to be. And if the world is going to, if hydrogen is going to play a part in decarbonizing the world, it could be that there's an opportunity here not that many years down the road. So what is needed? Awareness. You know, I point to 3 documents, and I'm sure there are others. They're all excited about manufacturing low carbon hydrogen without seeming to talk about the transportation challenges and opportunities around moving bulk hydrogen. So the purpose of this talk today is to try to create awareness around this transportation challenge, but more importantly, a potential opportunity. This opportunity would have to be grabbed by investors and business people who have a vision around where the puck is going to be. Any large change like this will require community support, so we need to create awareness within the community about why this is happening. Governments and agencies are producing, I said agencies, governments in Ontario and Alberta, as well as federal government, have produced these strategies. Quebec has one, though, and was prepared by Hydro-Quebec. And so if they're going to be successful in creating this hydrogen manufacturing capacity, we need to create the transportation infrastructure as well. And that's what we're talking about here. So where are we? The Bowman Center has identified this. Bowman Center has been working on hydrogen for about 5 years now. And a few years ago, we recognized that there's an issue with the density of hydrogen if we want to move it in long distances. And so that is why we had Queen's University do a study for us, as I mentioned earlier, and that study is available on request. And to further this initiative, we are developing a follow-up study that would look at liquid organic hydrogen carriers from the oil sands, gas oil. Now, let me just elaborate on this for just a second. Regardless of what you think of the oil sands, bitumen as it comes out of the ground, as bitumen, it's in the range of 70% asphalt. It's not just that it's asphalt, it's some of the best asphalt in the world. And so if you extracted the asphalt out of the bitumen, you would have this remaining gas oil. We think that the chemical precursors to manufacture different LOHCs, not just the ones we talked about, could be manufactured from this gas oil. And the asphalt, let's go back to that. We talked about electrification of transport. If there's less and less asphalt comes from refineries, as the demand for gas and diesel may wane over the next few years or so, where's the asphalt going to come from? Electric cars need roads, and so we make asphalt out of the bitumen, and we have the gas oil, and maybe one of the opportunities for would be to make these liquid organic hydrogen carriers from the gas oil component of bitumen rather than route it to fuels. Part of the scope of this study would be to design a conceptual process design for extracting or producing these liquid organic hydrogens from bitumen gas oil. We want to better understand the role these products would have in a circular economy. And with that, if you have any interest in this, please feel free to contact myself or Marshall Kern. We would really like to see if we can initiate some kind of a team or a committee to take a look at this with the intent of sometime in the not so distant future end up with steel on the ground. So with that, I'll be glad to take questions. I see we have a few in the chat. I'm not promising much in the way of answers, but we'll at least entertain the questions.
Thank you very much, Ed. Yep.
Okay.
I am Marshall Kern. I am the president of the Bowman Center for Sustainable Energy, and I'm really pleased that everybody has been able to join us and stay with us for so long through this conversation about liquid organic hydrogen carriers. There are several questions. A few of them have already been answered in the sidebar in the chat function, but Sid Jayaraman has a couple of questions. Ed and others may be able to answer this as well. Is there any work happening around shipping liquid organic hydrogen carriers via pipelines? Are there any limitations that you can see with this approach? And jumping to top of mind here, that yes, we do know that ammonia can be shipped by pipeline. It is being done so by pipeline in certain areas. There are there are economic limitations, but the being able to ship huge distances is a concern as well because of the economics. For methanol and toluene, these are also being shipped, including long distances by pipelines. There aren't any technical limitations, but it comes down to the economic limitations and being able to move from an area where it's being produced to where it is being consumed. So those are the kinds of limitations that we perceive at this point. For the other liquid organic hydrogen carriers that Ed has talked about, the dibenzyl toluene and so forth, there shouldn't be any kind of technical issue. It's a question then of the economics, how much would need to be moved from one place to another, and making sure that the proper facilities are in place in either location to prepare the material and to strip the hydrogen out, which gets, Sid, I think, to your second question. How mobile are these dehydrogenation plants? If they're anything like a reformer, you said you don't see them having any flexibility to move around to cater to various demand requirements. So please share any thoughts that we might have about a dehydrogenation plant for a hydrogen-rich hydrocarbon. Ed, can you speak to that? Have we focused, have you got some information about the dehydrogenation process?
Well, first of all, at the scale we're talking about, the plants wouldn't be mobile. The supply of the rich part of the couple would hydrogenate, make the rich version, and then load that into a pipeline or a truck or a ship or whatever, and send it off to the customer. The customer would have the dehydrogenation unit, or sometimes referred to as a reformer. In the case of toluene, might be called a platformer. And so the intent wouldn't be to have the dehydrogenation units mobile. They would be fixed facilities unless we're talking small scale. Like the hydrogenous units are quite small scale. They probably could be. I'm guessing they could be, but that's not the long term. I think the long term objective here would be to have, as in a refinery or in a chemical plant, um, fixed fixed units, large scale to make the economy work. I'd just like to make a comment though on this around shit. We're not. I'm going to say that there probably is work being done on liquid organic hydrogen carriers in Canada. We're just not aware of it. It seems like such a blatant, obvious thing to be looking at, and the gap, the unmet need is. It seems it's hard to imagine somebody isn't looking at this. But anyway, that's just an assumption. And as Marshall said, in terms of shipping either version of the two couples I referred to today as the LOHCs, the limitations are no different than they are for, in the case of toluene couple, no different than for gasoline. In the case of the DBT couple, no different than diesel fuel.
Thanks, Ed. And Chris Wallace has a similar question asking about the circular economy reference. Would we not be sending a ship full of toluene back to Canada to be refueled or rehydrogenated? Wouldn't this be the same as sending an empty LNG ship back to the refueling station? The initial thought that comes to my mind, Ed, and you can correct me and add to this, is that it becomes the question of economics because you're just repurposing an existing vessel. How does it move from location to location? And perhaps there's a place where the hydrogenated, or the hydrogen-rich liquid organic hydrogen carrier is being deposited, and then the ship is able to pick up another cargo and keep on moving around before it returns to the same spot. It's not necessarily going to be just a single ship moving back and forth between point A and point B. Is that your understanding as well, Ed?
Yeah, I don't. I thought I had intended to talk a little bit about this when I showed that slide. Yeah, the ship is being reused, and so is the chemical. So you can think of the chemical, the couple, depending on which way the ship is going. It's an asset. It's like the ship. It's an asset. You just reuse it over and over again. And so that's why I suggest it kind of looks like a component of a circular economy. In the case of liquefied natural gas, of course, the ship is going back to the customer empty. Well, there'll probably have to be ballast added to the ship for stability reasons, but in any case, this scenario would involve more fuel because the ship is not going back empty, as is the case with the LNG carrier. But that's why it's on our list of projects. The follow-up study is just how does this fit with the context of a circular economy? Maybe it's 90%, or maybe it is a pure perfect example. This is part of the scope of hopefully an upcoming study next year, and ideally, maybe some people on the call might be interested in participating in that.
Perhaps because Chris Wallace has asked a question about looking at the levelized cost for each of these carriers. Shipping ammonia is about 50% less expensive to ship than liquefied hydrogen and LOHC. However, there are still reconversion costs on the other side. So, Chris, it's a good question. If you'd like to participate with us in answering that, you're certainly welcome to reach out and chat with us, and we can begin to look at that in more detail. Yes, we recognize that levelized cost is one of the key things to look at as you are considering moving materials around. But Ed, can you add to that?
Yeah, one of the things we didn't really have time to go into this, but when you start talking about levelized cost, then what you have to also consider is the delivered product. I did mention it takes a lot of energy, and there are a lot of emissions associated with making ammonia, and I think to a lesser extent methanol, but never mind, they're nowhere near zero. If you take a look at, and then you have to, if we're going to strip the hydrogen, if you're going to use the ammonia as a fuel, ammonia wins hands down, same as methanol. But if you're going to strip the hydrogen out of the ammonia, now you're looking at another very energy intense process. And as part of levelized cost, you have to look at the net delivered product. What is it the customer's really after? In the case of liquid hydrogen, just to get the hydrogen into the liquid state will consume about 30% of the energy embedded in the hydrogen. And so the net energy delivered is actually lower than what I showed on the slides, because the slides that I showed were and the ship slide that showed petaJoules of energy, that was on board. but the net energy as part of a levelized cost or life cycle assessment, if you like, the amount of energy delivered in that case, net energy is quite a bit lower.
Okay. Brian Savadant has asked a couple of questions that indicate to me that he's really interested in learning a lot more about hydrogen. So Brian, I do hope you check our website. We do have several reports there. Please feel free to contact us. We can direct you how else to learn more about hydrogen. But you've asked about toluene as a known aromatic carcinogen. I think I've answered that to you in the chat function that IARC has given it its lowest classification for carcinogenicity, that it's not classifiable as a human carcinogen, but toluene as a hydrocarbon has a lot of other concerns regarding it. So it is well understood as an industrial chemical, and safety procedures are put in place. And I'm scrolling through, Brian, to just find your other question. Okay, how is hydrogen produced commercially? Right now, the majority of hydrogen certainly in Sarnia, is produced through a process called steam methane reforming, where natural gas is taken, put under pressure and with steam to break apart the natural gas to release the hydrogen and also separate out what's the remaining carbon dioxide. So that is the major way, but the other ways, there's a whole range of different ways to produce hydrogen. What we would like to focus on, and certainly a few others who are involved in the call would want to focus on, are what are called green hydrogen or low carbon hydrogen production systems, typically through electrolysis of water, which most of us have experienced in high school chemistry class. But the source of the chemistry would contribute to the carbon content or the carbon attributed to the hydrogen. Yes, you could have pure hydrogen, but how you achieve the hydrogen can have a carbon contribution. So again, Brian, we do have information on that on our website, and we're very happy to share that with you. And you've also asked a good question: why wouldn't Germany produce its own hydrogen? And the real key here is that Germany is planning to produce its own hydrogen because hydrogen has real applicability for some other industries where it's hard to decarbonize, such as steel and cement manufacturing. But the point is that Germany may not be able to produce enough hydrogen in the time frame that is needed. So the German government has come to Canada and elsewhere to set up these memorandums of understanding so that eventually, and we hope sooner rather than later, hydrogen that's produced in Canada would be able to be shipped to Germany for its kind of applications that are there. But please, Brian, feel free to contact us and we can follow up and share further information with you. Now, Ed, there's a technical question from Sam Supia. I hope I pronounced that correctly. What kinds of temperatures involved in hydrogenation and dehydrogenation?
So both these are catalytic processes to speed up the reactions. These conversions that I referred to. The temperatures are notionally. I'm a one significant digit engineer. Notionally between 200 and 300 degrees C. At relative the dehydrogenation is at fairly low pressure. The hydrogenation is at higher pressure. You're looking at a couple hundred degrees C with a catalyst appropriate to whether you're hydrogenating or dehydrogenating. Again, if you look up reformer technology, you'll get the dehydrogenation piece. If you look up solvents hydrogenation as a process, you will get more information. Now, I do have access to information if you want to contact me separately, but you're talking about something that has a fair amount of energy intensity associated with it. And so if you're going to maintain the green nature of the hydrogen, then you'll have to be using green sources of energy or low carbon sources of energy to drive these processes. Hope that answers your question.
Okay, and Dennis Bernhardt has asked a couple of questions. He asked an early one about ammonia, which I hope has been answered, Dennis, that ammonia can be used to carry hydrogen. There are different chemical processes and procedures to produce that. And ammonia has opportunities not just to carry hydrogen from one location to another, but it is a merchant quality material or merchant material, so that it has value in and of itself. But you've asked a couple of other questions, Dennis. How much?
Dennis, Marshall, I'm sorry to interrupt.
Yep.
I'm looking at Dennis. Does this use ammonia? So, Dennis, if we're talking about manufacturing liquid or organic hydrogen carriers, then we do not use ammonia for that. Ammonia is an inorganic chemical. We're talking about organic chemicals. So, if I'm under your question says, does this use ammonia? The answer, if you're talking in context of LOHCs, no.
Yeah. And I think that the question arose when you were sharing information about the movement of ships across oceans. There's a couple of follow-up questions and answers there added that ammonia does burn. It can be put into specialized engines to produce additional forms of power, including electrical power if necessary. But to my knowledge right now, there's at least in North America, these are still either pilot or single-purpose designed ammonia burning engines. I know that there's an answer that Maersk, the shipping line, is developing 14. John Ward has added that Maersk, pardon me, is building 14 ships using methanol as a fuel versus bunker oil. Why? Because it's in their analysis then safer and more economic than ammonia. It's also going to have essentially zero carbon emissions while at sea, so that it's looking at a particularly good opportunity there. But Dennis has asked a couple of questions about oils. So the first question is, how much DBT in a barrel of oil? Ed, can you answer that?
Nope. Dennis, that would be the objective of the first bullet on this follow-up study. I don't even know for sure. I suspect that there is, especially oil sands bitumen is highly aromatic. So it could be that there is DBT native in the gas oil. There could also be the hydrodibenzyltoluene native in the oil. We don't know. I don't know that anybody's ever even looked at it. But that will be part of the scope of the study. So profuse apologies. I don't know the answer to your question yet.
And I'm sure there's probably some smart organic chemist who has figured out a nifty, neat way to make dibenzyltoluene. So it's not just a simple matter of distillation to get it. There may be some neat ways to produce it.
Yeah, well, there are. This is in the present tense. People are manufacturing DBT today, not necessarily as a liquid, or as I mentioned in my earlier, DBT is commercially produced today, not in the volumes we're talking about here, but is being commercially produced. Is being produced because of its high stability and resistance. It's thermally stable as well as and remember what I said. It's $5 a liter, or sorry, a kilogram. Well, it's practically the same thing. It's $5 a kilogram compared to toluene. The price of gasoline is kind of close to $1. Sorry, not anywhere near that. So just to drive home the point, DBT is being made today. We know it, not me personally. We're going to find out, but the industry knows how to make this. It is not something that we need a whole bunch of research to come up with a whole new synthesis scheme.
Okay, I'm going to wrap this up. I think I've answered all the questions or asked all the questions, Ed, that were put into the chat function. Anybody who wishes to reach out to us, please do so through our website, bowmancenter.com. You can reach directly to me because I've sent out a tremendous number of emails to invite people to this webinar. And we are going to be focusing on trying to push this forward as a positive economic opportunity for Canada and for Sarnia in particular. This isn't the end of the process. We aren't saying this is done. We have opportunities to go further. So I invite anybody who wishes to connect with us and find out a way that you can work with us so that we can participate on this kind of study and promote hydrogen and hydrogen consumption and use in Canada more completely. With that, on behalf of the Bowman Center for Sustainable Energy, I sincerely thank Ed for the time and energy to put this together. I thank Don Greaves, our Vice President, for the technical support in making sure that this is delivered so smoothly and recorded so that it will be available on our website fairly soon. And I hope everybody has a very pleasant and very safe day. Thank you very much.